Hey everybody, welcome back. We're getting right back into our environmental science studies today with a look at the planet Earth. The reason why we have to look at Earth and what it does and how it behaves is because it's the environmental canvas. Everything else is reacting to what the Earth is. And so we need to talk about it a little bit. Now, we actually have a very long series already on this channel on Earth Science X. You can click there and then you can see an entire series that deals with many of the things that we're going to just hit on just very quickly in this lecture. But if you're just interested in the environmental studies aspect of this particular topic, then you can stay right here and we'll cover most of those things, the highlights, really quickly. So geology is the basis for environmental science. The reason why is because everything in the environment is responding to physical processes that are either above, at, or below the Earth's surface. These processes, they control the shape of the landscape, they lay the foundation for the environmental systems and life, they provide raw materials for industries such as iron, copper, and steel, they provide energy from fossil fuels and geothermal sources. All of this is in the processes that the Earth is wrapped up in, between the Earth and actually the Sun, of course. As we discussed in our last lecture, ultimately fossil fuels are trapped sunlight, right? Those are old living organisms that went through photosynthesis, and that energy is then trapped into the petroleum reserves on Earth. And the way that we go about studying the Earth is through a science called geology. Geology is the study of Earth's physical features, processes, and and history. A human lifetime is just a blink of eye in geologic time. The Earth is really old. It's about 4.5 billion years old, and a lot can happen in 4.5 billion years. And in fact, on Earth, a lot has happened. So here we see the Earth as it exists today. This is a photograph that was taken, or that I actually collected from Wikipedia on May 30th, 2020. So this is a fairly recent image. But if we were to look at pictures of the Earth from, say, 60 million years ago, 100 million years ago, a billion years ago, it would look very different than what we're seeing on this image. We're going to get into that here in a moment. Now, the way that the Earth is set up right now is that it has a series of layers in it. When the Earth was originally formed, a lot of people believe it was all homogeneous, it was all mixed up, but since then it's settled out, almost like the way that oil and vinegar settle out in salad dressing. So the Earth is consisted of layers. There's something called the core at the very center. This is very dense. It's made out of nickel and iron material. It's believed to be an alloy of these things. And there's two phases of the core. There's the very center of the Earth where the inner core is, and it's a solid sphere. It's a sphere of solid nickel and iron. Around that is the outer core. And the outer core is molten. It's a shell around the inner core that is in constant flow within the Earth. So it is swirling around. And when we look at this diagram over here, here we see the solid sphere in the middle. This is the inner core. Outside around it, this is the outer core. It's liquid iron and nickel swirling around. And some people actually believe it's moving around at pretty quick velocity. Around this liquid outer core that we see here, also up in this image here, is the mantle. The mantle is less dense. Gravity doesn't pull it down as effectively, so it sits a little bit higher. It's still pretty dense compared to the rocks we have up here on the surface, but they're less dense than the core. They're less dense. It's elastic rock composed of mainly silicon and aluminum oxide minerals. Some of the minerals will be familiar to you. Mainly minerals like, especially in the upper part of it, feldspar. Represents most of Earth's volume, and it contains most of the radioactive elements that keeps Earth's interior very hot, especially thorium. There's uranium in there, but thorium is another big one. And also included in this is something called the asthenosphere. Now, the asthenosphere is very soft or melted rock located just below the lithosphere, which we haven't talked about here in a minute. So the mantle is this big, large section right here, right? So here's the mantle right up to the top of something called the crust. And the crust actually has this red layer right in here, the asthenosphere. And it's pretty soft. Now, the material above it is actually rigid and hard. The material down below it is actually relatively rigid and hard. I mean, it's elastic, but this is actually very, very soft. And in some cases, almost to the point of actually melting. It's very, very close to that point. So this is soft and this is rigid up here on top. And the mantle itself is the source of most geothermal energy on Earth. Iron and nickel is not radioactive, so most of the radioactive elements are not believed to be radiating their heat from here. We believe that most of it's actually coming from the mantle, and that's where the heat budget for the Earth is coming from. We'll get into that here in a short period of time. So think about this. We've got a very solid iron-nickel core, a liquid convecting, we're going to get into what convection is a little bit later on, but convecting iron-nickel outer core, a rigid mantle. But right at the edge of that mantle, right at the edge there's this thing called the asthenosphere, and sitting on top of the asthenosphere is the lithosphere. Lithosphere is something a little bit different. So the crust is the thin, brittle, low-density layer of rock sitting on the top. That's where we are right now, sitting on top of the crust. And the crust is also part of the lithosphere. It's the uppermost mantle and the crust. So here's the mantle all the way up to that black line where the lithosphere starts. We got crust up here, or I'm sorry, we got mantle up here. And so we got asthenosphere and then upper mantle right here. That means that the upper part of the mantle is soft and gooey, is a good way of thinking of it, whereas down below it is a little bit more rigid, and then there's a crunchy top up here on the top. That's the crust and the lithosphere up at the top. All right. That's important because when we look at the Earth, we've discovered some really fascinating things since especially the 1960s. And one of the main things that we've discovered is the concept of plate tectonics. Plate tectonics is the recognition that the Earth's lithosphere, it's that crunchy part up on the surface, the very top of the Earth, is fractured and composed of numerous continually moving plates. Currently, there are 7 major plates. Right, you can see them. Here's the Pacific plate, the North American plate, the Eurasian plate, the African plate, South American plate, and the Antarctic plate. And several dozen microplates. The Juan de Fuca is one of these, and you can find them actually here, small versions of them on this diagram represented, have been identified on Earth. So the Earth is just fractured up. And so if we just think of the main 7 major plates moving around over time, you realize that things are going to get pretty interesting. And we've noticed that there's some interesting associations. Like there's a close association between plate edges. So here's a plate right here. This is the Pacific plate. And volcanoes, sure enough. Here's the edge of the plate, and those little purple triangles that we see on here are volcanoes. These are actually volcanoes that exist at the surface. These are not the undersea volcanoes. These are the ones that we just see up here at the surface. We also get earthquakes at those locations. These are where the epicenters of many earthquakes occur, is right on that edge. And other violent events on Earth, tsunamis, for example. An example of this is right here. Here's Japan. Japan was hit by a tsunami roughly 10 years ago. And the effect has been the shutdown of the Fukushima nuclear power plant, which actually went into meltdown. Right along Japan here, right from eastern Russia on the Kamchatka Peninsula, we see a series of volcanoes. There's, in addition to the volcanoes, there's earthquake epicenters here, very large ones all the time, and we get the tsunamis as well. So that association turns out is not accidental. And we're going to get into that here in a moment when we go step by step through what these edges are. But notice out here, it's kind of boring. I mean, Hawaii is out here, but Hawaii, it turns out, is an aberration. It's an anomaly. Most of the time, volcanoes occur right along the plate boundaries. All right, so the question of how in the world does the lithosphere, those plates, how do those move around on the surface? What actually motivates that to occur? And the current thinking is this concept of mantle convection. In other words, it's the lithosphere that's floating on top of something that's happening down even deeper in the Earth. So the mantle convection concept is the very slow creeping motion of Earth's solid silicate mantle. So silicates, those include your feldspars that I mentioned earlier. Those are the minerals that we find in those rocks down in the mantle. Silicate mantle caused by convection currents carrying heat from the interior to the planet's surface. Okay, so there's a couple of sources of heat down in the Earth. There's radioactive heat from the mantle, and that's estimated at between 15 and 41 terawatts, and primordial heat, which is between 12 and 30 terawatts, which drive the convection current. So the Earth has radioactivity within it that's always driving, that drives a need for the heat to escape. It's just a thermodynamic process. We actually talked about that a little bit when we talked about entropy. So we have heat here in the mantle, and it wants to escape out to the cooler portions of the surface of the Earth. All right. So this radioactive heat is one source. Primordial heat, basically when the Earth was formed, you have these large objects slamming into each other as the Earth accumulated all this material. And when you take two very large objects and drive them together, you can actually produce a lot of heat energy in that way. You're basically converting energy from the motion of the object into heat energy through the collision. Okay, so things get really hot, it turns out, when you do this. What happens is it pushes the mantle's soft rock up. So the mantle, as we talked about, it can be especially gooey up here at the top. But over very long periods of time, the elastic mantle is actually able to circulate in a convection cell. So here's the outer core, here's the lithosphere up here at the top. And so it's pushing right here. Here we see that push right there, like a conveyor belt. And let's see here, pushes the mantle's soft rock up as it warms and down as it cools like a conveyor belt. So here we see it moving down. The lithosphere is dragged along with the mantle. Okay, so as the mantle moves, the lithosphere is experiencing force. In this case, there's a force that's trying to pull the lithosphere in this direction, and on the other side, it's trying to pull it in this direction. Okay, that's the concept that we see here. Now over here on the side, we see that this one and this one are coming together. So there's actually a force pushing this one and this one together. Okay, the idea of how convection works, a good example that you might see in life is just when you boil water in a pot. So that's what we have up over here is we got this boiling pot up here on the top. The water down at the bottom gets really hot. It circulates up to the top, releases its heat, drops back down, and it just keeps circulating around. And when you do that, you get things moving around at the surface. That brings about a concept called Pangaea, which means all land, and Panthalassa. Panthalassa is the concept of all one world ocean. So Pangaea is all land masses being joined together to a supercontinent 225 million years ago. So the continents, we do believe, have combined, separated, and recombined over millions of years, even billions of years. And this is just an example of what we think has happened just over the last, say, 200 million years. Now, the Earth, again, is 4.5 or 4.6 billion years old when we round it up. 4.6 billion years old. So this process of continents being large and breaking up and then reaccumulating into other large continents again has probably happened over and over and over again. Okay, so this is what we believe the Earth looked like about 200 million years ago, and this is how it would have broken up into its current orientation today. All right, so what we need to do now is explore the way that these plates can move around on the surface of the Earth and how they tend to interact. It turns out there's 3 different ways they can do it. One way is they can diverge. In other words, the plates have the ability to move away from each other, as we demonstrated on the previous slide. So it turns out there's some pretty interesting things that tend to happen at divergent plate boundaries. One of the most famous plate boundaries, divergent plate boundaries, goes right through the middle of the Atlantic Ocean. And this is the divergent plate boundary that separated South America and Africa from each other about 200 million years ago. So when this happens, plates are moving apart and forming large rift valleys. These rift valleys can be quite deep, they could be quite magnificent, but most of the time they're at the bottom of the ocean. Sometimes we get lucky and they actually wind up at the surface. There's a rift valley, if we look here at this mid-ocean rift right here, this is Iceland. Iceland is right up here at the wrong location. So here's Iceland. And so you can see that rift is going to go right through the middle of the island, and sure enough, that's what we're seeing here. These are divers in the mid-Atlantic rift zone going through Iceland. So the rift right here is in shallow water, and so you're able to come in here. On one side is the North American plate, on the other side is the Eurasian plate. And basically, the Earth is splitting right here. It's amazing. So what happens at these locations? Well, magma rises into the rifts. So magma is molten rock. We're going to talk a little bit more about what magma is when we get to volcanoes a little bit later on, but it's molten rock that rises into the rifts to the surface and creates new crust when it solidifies. Basically, when you have magma that rises up and fills into this gap, it interacts with the seawater. The seawater immediately quenches it and cools it into rock right away. Because these rifts are made of young, hot rock, in other words, this whole thing will still be hot even though it's in cold water. It'll be a lot hotter than the rocks around it because it's right next to a large, what we call magma chamber. They sit high on the Earth's surface, forming long chains of undersea mountains with a central rift valley. And this is simply because when things are hotter, they are less dense. And things that are less dense, they sit higher. So when we look back on this picture of the Earth again, this mid-Atlantic Rift Valley, that's right here in the middle, the big rift zone, it also happens to sit right on the top of a large mountain chain, the largest mountain chain on planet Earth. Okay, and it just turns out that Iceland is sitting right on top of it. And underwater volcanoes and hydrothermal vents are very common. In terms of earthquakes, there are little earthquakes that happen out here, but they don't tend to be very, very large. But there are a lot of volcanoes here. The vast majority, in fact, of volcanoes occur at these mid-ocean rift zones. All right. Another way that plates can interact with one another is through collisions, right? So instead of moving away, if they're moving away here, then they have to be running into each other somewhere else. And it does turn out that there are 3 different ways that they can collide. And this is based on the fact that there are 3 different kinds of crust that can run into each other. The 3 kinds of convergent boundaries are ocean to continent. In other words, the oceans, which are made on a different kind of crust than the continents are, it tends to be denser and it sits lower. When you run an ocean into the continent, something very interesting happens. You can take an ocean, you can run it into another ocean crust. When that happens, something interesting happens. We'll talk about the rules for that here in a moment. And then there's when continents run into other continents. In order to understand what's going to happen here, we have to understand this concept of subduction. So subduction is a process in which the oceanic plate slides beneath less dense crust. In other words, when you have 2 things running into each other, something's got to make space for the other thing. And there's only 2 ways to go. You can go over or you can go under, right? So subduction is when it goes under. And remember, if the oceanic crust is denser, it can actually just drive itself right underneath the other plate. So ocean crust, it turns out as a rule, is always subducted beneath continental crust, with rare exceptions, right? There's something called abduction. This is where occasionally the oceanic crust is scraped off and moved on to the edge of the continent. But for the most part, continental crust, which is 10% less dense than oceanic crust, will tend to not subduct, whereas the oceanic crust will almost always go under. Now, what about if we have 2 bits of oceanic crust? Well, older, colder, that's right. If we go back to this old image over here, the red zone is the young, hot rock here. This is where all the volcanoes are. As it spreads away from here, the rocks get younger, they get colder, and they sit lower because they become more dense. So older, colder oceanic crust always subducts beneath younger, hotter ocean crust. So sorry about this. This is a typo in the slide. And continental crust does not subduct. When 2 continents collide, under scenario number 3, when 2 continents collide, that's a clear-cut case for something different is going to happen. We're going to get into that in a moment. All right. So when ocean to continent convergence occurs, there's a couple things that happen. First, the oceanic crust subducts beneath the continental crust. So here we have the lithosphere, here's that asthenosphere. Remember, the asthenosphere is slick. It allows things to move and slide up on top of it. The lithosphere, sitting on top of it, is going to move and subduct beneath the continental crust that we see over here. The continental crust is thicker, it's less dense, it's just not going to go under. It's sitting at the Earth's surface for a reason. And what happens is the oceanic crust will get recycled back into the mantle. So this will come down, it'll arch and bend its way down into the Earth, and basically be recycled into the Earth. Right alongside that, it will typically form a long, deep trench where the seafloor bends and slides beneath the continent. That trench in this image is right here. So that trench occurs right where the lithosphere bends. The oceanic lithosphere will bend and go right down into the Earth. And it may have something called an accretionary prism. Not always, but it might have it. An accretionary prism is when you have a bunch of oceanic sediment, I don't know, sand, clay, silt, material washed from rivers out into the trench. It might get scraped up and accumulated in the trench. That's what we mean by an accretionary prism. Not all the time does it exist, but sometimes it's there. Okay, I would say most of the time there's a little bit at least, but there are moments where it's not. There tends to also be explosive volcanoes like Mount St. Helens. Here we see what happens here is the lithosphere, the oceanic lithosphere or the oceanic crust will then be subducted onto the lithosphere. And the oceanic crust has a lot of water in it. And it turns out that water, when it's mixed with rock at very high heat, will lower the melting point of rock. And so rocks down here that you can see the rocks right here, right where I have the cursor, don't melt, but the ones over here do. And that's because there's water mixed into it. So when you lower the melting point of rocks, they'll tend to flash into magma, and that magma will rise, right? Liquids tend to rise because they're less solid on average. So that magma will rise and will form a volcano. This is really just the way of the water trying to get its way back up to the Earth's surface. And because there's water, they tend to be explosive, right? Steam explosions tend to happen. Massive earthquakes and tsunamis are also very common. I mean, you can imagine if you're going to take the entire part of the crust and shove it underneath an entire other part of the crust, you're going to get massive earthquakes. And in fact, these can be quite large, magnitude 9 or larger sometimes. Another way that we can move them together is instead of taking the continent and the ocean, we can actually take two bits of the ocean and converge them. So we get ocean-to-ocean convergence. And this is actually pretty common too, it turns out. We just don't always interact with it as much as we're accustomed to because we don't live in the oceans on average as much as we live on the continents. But it does happen. What we tend to see is that older oceanic crust subducts beneath younger, hotter oceanic crust. I always say old and cold subducts beneath young and hot. That's just how it is. What we see here is a subduction zone. This right here, the little pluses here are the zones of earthquakes. So we can actually see where earthquakes are generated as this plate is subducted and recycled back beneath the asthenosphere. And what it'll do is it'll form typically 3 different lines that we see at the surface of the Earth. So you might get an accretionary prism. Remember, that's that stuff scraped off as it's going down, and it builds a big pile up at the top. So those are the scrapings as this plate subducts down underneath this other one over here. It'll also form a volcanic line, something we call a volcanic arc. So you'll get the accretionary prism here, you'll get the volcanic line here. And this is where you get that volcanism. Just like we saw over here, same thing is happening, but it's happening here. It's a different chemistry for the most part, and you get it in different locations. But you can get pretty amazing volcanic systems when this occurs. These systems typically also are associated with long, deep trenches where the seafloor bends and slides beneath something called the volcanic arc. We're going to talk about that right here. These are amongst the largest features on Earth. Let me give you an example of where this happens. This is Guam. Guam is 1,332 feet above sea level. It's located right here. It's this little island. There's a major U.S. military base located there. And you can see right next to it, here's the Marianas Trench. And right next to it is Challenger Deep, which is located about right here. This is an approximation. Challenger Deep is 35,827 feet deep. This is deeper than Mount Everest is tall. So Mount Everest, if memory serves, is 29,029 feet. You might want to check me on that, but I think that's the right height. That's enough distance for you to put the top of the Himalayan mountains with Mount Everest into the bottom of the Challenger Deep, and there'd still be over a mile of water just to get to the beach. And then to get to the top of Guam is 1,332 feet. So if we start here and we start working up this embankment all the way till we hit the top of Guam, the highest elevation at the volcano located right over here, we're talking about almost 3,700, over 37,000 feet of elevation change. I mean, that's for jetliners. I mean, they fly even sometimes not even that high. So we're talking about very, very, very deep, all the way to extremely high in terms of this feature. If the ocean wasn't there, you'd see it. It would be one of the largest features on Earth. Okay. Massive earthquakes and tsunamis are also quite common in these situations. And we're going to get into why, again, how tsunamis come about. But I mean, when you have a plate jamming itself underneath another plate, you're going to get massive earthquakes. And here's that trench where this is happening. This is the Pacific plate happening right here, and it's just jamming itself into that trench. All right, the third way that you can move things together is by colliding two bits of continental crust. Okay, so when that happens, there's no subduction. So continents tend to just pile up on top of each other. It just turns into just a huge mess. And the result is huge mountain chains, right? So you can't get one to really go down. I mean, you can force one on top of the other, but it's not going to recycle itself and subduct itself down into the earth and become part of the mantle again. They'll just simply layer on top of each other. They'll pile up and they'll deform. The rocks will fold. Large faults will form. And you'll create these massive chains of mountains. The Himalaya are an example. The Alps and the Appalachian Mountains in the United States, all formed in this way. What we see here, this is an image. This is the Indian plate. It's colliding with the Eurasian plate right here. And what it's done is, in fact, it's moving in this direction. The Eurasian plate is moving roughly in the southerly direction. And as they collide into one another, massive faults are forming right along this edge right here and pushing and ramping a huge amount of rock straight up. Mount Everest is located right here at 29,000. Oh, there it is, 29,029 feet. I challenged you earlier to check my altitude, but there it is. It's located right here. To give you another idea, this is the inset over here of that location is right here, showing you how tall these things are. These mountains are tall, they're rugged. Massive earthquakes are very common along these types of plate edges, and they're very, very dangerous places to live. There could be large landslides, there's flooding events, and of course the earthquakes are a major problem as well. This entire part here, the Tibetan Plateau, has been crushed between Asia and India as they've been colliding one with another, and so the entire area has been lifting itself up. Normally rivers and lakes tend to try to find a way to drain out to the ocean. Well, as these faults and as this stuff rises up, it actually pinches off the way for this water to get out. So you have permanent lake systems setting themselves up here on top of the Tibetan Plateau. There's no external drainage is what I'm trying to say. These mountains are rising so fast they're preventing the rivers from successfully draining these areas. All right, so we've talked about the way that plates can move away from each other and how they can move towards each other. There's a third way that they can move, which is side by side. Okay, and those are referred to as transform plate boundaries. And in a lot of ways, transform plate boundaries are the most benign, but they also tend to be in areas that human beings like to populate a lot. The city of Los Angeles immediately comes to mind as a place where this happens. So transform plate boundaries where two plates meet, slipping and grinding past one another. Friction spawns earthquakes along strike-slip faults. So strike-slip faults means that you've got two faults, or you've got two sides of the earth, or two sides of the crust, and they're trying to slip, and every once in a while the friction releases, and boom, it moves very, very quickly. Now, the types of crust don't matter as much as in collisions. In collisions, if it's oceanic or if it's continental, it's a really big deal. It turns out, for example, the San Andreas Fault is moving oceanic crust for the most part right adjacent to continental crust. So they're two different kinds of crusts in very close proximity, moving one past each other. And in fact, there's some transference. A little bit of North America is sometimes transferred over to the Pacific crust side or to the Pacific plate side, and vice versa. So it's not a simple situation, but you get the idea here. And what we see here is on this side of the fault, this is the San Andreas moving right through here. This is the Carrizo Plain, which is located just north of Los Angeles. And here, this entire side is moving in this direction. This side is moving in this direction. And we can even see that this river right here, this wash, is moving across. It's actually dog-legged as it's trying to keep up with the motion of the fault. So whenever the fault moves, it actually cuts off, or what we call beheads, portions of this. So you can see old places where the river used to be, it's been cut off and translated up over here as it slid. So it's kind of cool. So plate tectonics is a big deal. I mean, it's responsible for all the landforms that we see, or most of the landforms that we see. Tectonics builds mountains, it shapes the geography, it tells us where the oceans are going to be, it determines where a lot of the islands and continents are going to be located on Earth, and it gives rise to earthquakes and volcanoes, all of which are important natural phenomenon that as environmental scientists we need to keep track of. Now, topography created by tectonics also shapes climate. So when we talk about topography, this is changes in elevation. Where the mountains are, that's a change in the topography. So high topography means areas that are of high elevation. Areas of low topography are areas of low elevation. So if it turns out that if you have mountain ranges in the way, that alters the patterns of rain, wind, currents, heating, and cooling. So for example, here we have mountain ranges here, and this is the Gulf of Mexico taken by a Google Earth image. And we see the Sonoran Desert located right over here. But notice that we have an area of green located over here on coastal Mexico, and that is largely a phenomenon of the topography. And of course, that affects the location of biomes, where things live, where plants and animals live. Different things live here than live here as a consequence of where those mountains are. All right, so we've been talking about rocks and minerals. We'll just do a quick discussion. I mean, super quick discussion of what a rock and a mineral is. So a mineral is any element or any inorganic compound. It has a crystalline structure, a specific chemical composition, and distinct physical properties. So it's something that has always got the same stuff. So silicon dioxide is quartz, SiO2. It's always going to be SiO2. That's what they mean by it having a specific chemical structure. And they're crystals. And they have distinct physical properties. We know their hardness, we know something about their color, you get the drift. Here are some really amazing, these are, both of these are in fact are opals here. This is a Luz opal with something called a galaxy inside. It's an incredible little feature. I found this just surfing on the web and I wanted to share it with you. And then there was another one on the same website over here. This is a rounded sunset fire opal. Again, these are minerals, they're hydrated silicon dioxide minerals called opal that makes this amazing color. It turns out there are thousands of minerals, but we just want to simply mention what they are. It's where all those atoms that we talked about in the previous lecture wind up on Earth. Okay. Now a rock, by contrast with a mineral, is an aggregation of minerals. So it's one or more minerals, or it's actually several minerals, so an aggregation of two or more, I should say, minerals in a single substance. So these are rocks right here, right? There's actually some pretty interesting stuff happening here, but you can see that these little bands in here, these are little microscopic crystals that we see everywhere that create all of these rocks. And in this case, this looks like a nice piece of opal-rich material over here, a rock called a chert. All of this are accumulations or agglomerations of minerals into single blobs of material that we call, in this case, a cobble. So these are cobbles that are probably washed along a beach. Again, this is a figure I found online and I just liked it and wanted to share it. Now, it turns out there's three different kinds of rocks on Earth. There's igneous rocks, there's sedimentary rocks, and metamorphic rocks. And you probably have heard of those different rock types before, but we're going to go over them just briefly. So an igneous rock is formed when magma cools. Igneous rocks are what we can think of as born of fire. It even has the word the Ig in there, it's where we get the word ignite and all these other things. It's from the same prime root as fire. So igneous rocks form when magma cools. Magma is just simply molten liquid rock within the earth. So intrusive igneous rock is magma that cools slowly beneath the Earth's surface. Granites form this way. This is where the liquid it's a liquid down in the earth, but it doesn't make its way to the surface. It cools down below. And if it cools down below, it'll crystallize into nice, beautiful rocks like granites. Here's an example of a place where that might happen. A laccolith is a place where we might expect this to happen. We might have a sill that comes in and fills in a blister of magma, and that magma never makes its way up into the surface, so it crystallizes down below. Whereas we have extrusive igneous rock, this is magma ejected from a volcano. So basalts, like in Hawaii, those black lava or those black rocks that we see in Hawaii are extruded or extrusive igneous rocks, and those wind up at the surface. And that can also result in steam, gas, ash, create volcanic craters. Lots of stuff going on with volcanoes. And by the way, there's a whole lecture that I have on my Earth Science X website, or I'm sorry, YouTube channel. Check that out on volcanoes if you're interested in how volcanoes work. Lava, of course, is the same thing as magma, except it's magma that is released from the lithosphere. So once magma comes out of the magma chamber, in this case of a volcano, and makes its way to the surface, these gases separate out, and the lava is the liquid portion that comes out of the magma. So the magma is the combination of lava plus the gases, whereas when it gets to the surface, the lava separates out. So that's the reason why we have different terms for them. Sedimentary rocks, I have to admit I'm a little bit biased. I really love sedimentary rocks. These are rocks that are born of wind and water. They're amazing. They come in such a wide variety of colors. The minerals that we showed you, the Lewis opal and the fire opal, are actually from sedimentary rocks. And they are absolutely amazing. So sedimentary rocks are formed when sediments are compacted or cemented, which is to say dissolved minerals crystallize and bind together. So typical forms of sedimentary rock include sandstone, limestone, shale, mudstones. You can think of all of those things as sedimentary rocks. And what happens is when you get little bits of material, and sometimes fossils are included in that, you can compact and lithify and create a rock through, by the way, that process is called lithification. And frequently they exhibit clear layering. Now you don't normally find layering in the traditional sense in igneous rocks. You might, if you look at the ash flow layers, that can happen. But traditionally we think of layers as a sedimentary feature. So this is a photograph of Bryce Canyon National Park. This is an absolutely amazing place to go and visit and hike around. You can check it out in a day. These beautiful spires are caused by differential erosion happening in sedimentary layers. And probably the prettiest, and granted that's a very subjective thing to say, but the prettiest rocks are the metamorphic rocks. These are born of heat and pressure. High temperature tends to reshape crystals. I mean, if you take a crystal and you put it under enough heat, it'll do one of two things. It'll either melt or it'll recrystallize to something that is more, how would you say, more stable at those higher temperatures. A classic example of minerals that do this is diamond and graphite. Graphite at the Earth's surface is perfectly happy, but diamond is this very hard, dense material, but it turns out that it's actually really happy being at high pressure and high temperature within the Earth. And so it will degrade into graphite at the surface if it can. Now, if I take graphite and I put it under extreme heat and pressure and put it back down into the Earth, it will convert into diamond. Okay. Now the real rule for this, or the big rule for this, is I can't put it under such high heat that it melts. It has to be at high pressure and high temperature, but not so high that it actually melts it. Okay. A common feature that we see in metamorphic rocks is banding or foliation. So common metamorphic rocks include marble, which is actually pressure and heated limestone, and slate, which is heated and pressurized shale. These are types of metamorphic rocks called banded gneisses. They're actually in a big pile of boulders. I'm not exactly sure where this image was taken, but they're all banded gneisses, which are really beautiful, high-grade metamorphic rocks. These have been under very high pressure and temperature. All right, so we mentioned all of that to kind of get to this concept here. We talked about how plates move together, how plates pull apart, how they slide past one another, the three different kinds of rocks. And what we wanted to do is show that those are all connected, that there's a relationship that exists between all of them, that the Earth is in fact not only just recycling crust all the time, especially oceanic crust, but all the rocks within it as well. And so that results in something called the rock cycle, which is the heating, melting, cooling, breaking, and a reassembling of rocks and minerals over very long periods of time. So rocks and minerals are constantly being reformed and recycled on Earth. It's happening right now. What do you think volcanoes are doing? Right? Volcanoes are forming new rocks today. Mid-ocean ridges are spreading and volcanic materials coming in. Subduction is pulling rocks back into the Earth. It's recycling this right now as we sit in the environment that we're watching this video on. And understanding the rock cycle helps us appreciate the formation and conservation of soils, minerals, fossil fuels, and other natural resources. When we think about soils, we don't necessarily think about how long it's been there or what it takes to make them or what type of rock is required to exist for that type of soil to form. So we have to be kind of mindful of these things. And so the rock cycle is right here. Over here to the right, we actually see the rock cycle as it is deployed in a convergent plate boundary. This is where we see an oceanic crust being subducted beneath a continental crust. And so here we have sedimentary rock. This is sedimentary rock. These are sediments that are washing in through rivers out of these mountains. This sediment is coming in on the beach. It's actually falling down into what is eventually the trench. It's being compacted, so it's going under pressure. As it's being put under pressure, it's being pulled through this conveyor belt system, right? Because we have subduction happening. It's now being converted into metamorphic rock. As it's going under higher pressure and temperature, it might be uplifted. We might actually see it up over here. But as it goes from metamorphic, it'll transition into a melting zone. That melting metamorphic rock will then turn into igneous rock. That igneous rock will then go up into the volcanoes, and the volcanoes will then suddenly be subjected to weathering. That weathering will then result in the formation of sediments, and it'll cycle back through this process over and over and over again. So that's what we mean by the rock cycle and its connection to plate tectonics. And by the way, all of the different plate boundaries have forms of the rock cycle happening around them. All right, so really quickly, I would like to talk about some of the phenomena that happen at these plate boundaries. And chief amongst them is earthquakes. Those are pretty uniform at all the different plate boundaries. Sometimes they're large, sometimes they're small. So all an earthquake is a release of energy along a plate boundary or a fault, right? So faults are where energy is being transmitted across the landscape from one boundary, frequently from one boundary to another. That can be along a transform fault, for example. They can do tremendous damage to life and property. This is actually an image of an earthquake that happened, a 6.6 in central Italy that happened, and you could see what that magnitude 6.6 did to this town. It was absolutely destructive. Now, buildings can be built or retrofitted to decrease damage. And buildings are designed, but the buildings are not designed to be flexible. I mean, we can design them better, right? We can design them to swing. What's really interesting is this clock tower actually survived, and I believe the clock tower had some seismic countermeasures built into it, if I can remember from the original news article that I saw this image in. It's expensive. Buildings in many poorer nations do not have such protections. Now, another thing that we see over and over again are volcanoes. So volcanoes are formed when molten rock, hot gas, or ash erupts through Earth's surface, cooling and creating a mountain. Up here, we actually see an image of a volcano called Mount Unzen. We see this cloud coming off of it. It turns out this is something called a pyroclastic cloud, or pyroclastic flow. So what happens is that lava can flow slowly or erupt suddenly, right? So there's different ways that lavas flow, and if you go into my series on Earth Science X and study the origins of volcanoes, the origins of igneous rocks, you'll understand what I mean by how the different ways that lava chemistry can affect the explosiveness of a volcano. Now, one thing that we do know that is a big deal are these pyroclastic flows. These are fast-moving clouds of gas, ash, and rock, and they can kill people, and they do all the time. In fact, this particular event that was caught on a news camera did kill people. We actually see this guy here running from it as this thing piles into the town. And this is from Mount Unzen in Japan, 1991. So volcanic eruptions exert environmental impacts. Ash blocks sunlight, and sulfur emissions lead to sulfuric acid, blocking radiation, cooling the temperature. But that's natural. This happens all the time. What I want to do is I want to show you this animation of this pyroclastic flow while this guy runs away from it. So it's coming down into the town, and they are just driving as fast as they can to get away from it. And it's going to cut off here in a moment. Okay. So these things are extremely dangerous, and they're hot. It's full of ash. This ash is extremely toxic to human beings, and so it's dangerous stuff. Another thing that tends to happen is landslides, right? When you have big mountains in the area, what goes up must come down. And so if you have large amounts of material that's standing really, really high, sometimes you don't need to wait for the wind or the water to come and wash it. Sometimes gravity just takes it. So that's a landslide. This is where we see something called a severe sudden mass wasting. This is mass just wasting its way down the hill slope. Large amounts of rock or soil collapse and flow downhill. So mass wasting is the downslope movement of soil and rock due to gravity. So rain saturates soils and trigger mudslides. That's one form of mass wasting. Mass wasting is the erosion of unstable hill slopes, and it tends to damage property caused by humans when soil is loose or exposed, and can cause massive damage. Mudslides after Hurricane Mitch killed over 11,000 people in 1998. Let's look to see what this slide is, because if you saw one happening, you might think to yourself, well, I can just get out of the way of it. Well, watch this. Here we actually see it moving, and the entire hill slope is now moving at a very high speed. You can't run past that. And if you got caught in it, you would almost certainly be killed. Another important phenomenon that we're really developing an appreciation for right now are tsunamis. So tsunamis tend to follow earthquakes, volcanoes, and landslides. And all it is simply a surge of seawater that's caused when huge volumes of water are displaced by earthquakes, volcanoes, or landslides. That's what they are. So you can have a large landslide that goes into the ocean. It's going to create a giant wave when that happens. The damage can be really widespread and often across to distant coastlines. So here we actually see the tsunami aftermath. This all used to be forested area. In fact, there were people living here. There was a city down here. It's been completely wiped away by tsunami that came in here and ripped this entire forest right back out to sea. This was the December 2004, the December 26th, 2004 tsunami event that came in. And I believe over 250,000 people lost their lives, not just here, but across the world, across the Indian Ocean, as a result of that tsunami. It was an amazing force force of nature that went out that day. Coral reefs, coastal forests, and wetlands can be damaged. I mean, there's nothing here, right? If there was any coral reef here, it's definitely been impacted. Saltwater contamination makes it hard to restore them. I mean, if you have a bunch of fresh water here and you dump a bunch of salt water on it, it tends to damage this coastline, right? It takes a while for it to flush all that out, and you could see the mess that comes from this. Agencies and nations have increased efforts to give residents advance warning of approaching tsunamis, and preserving coral reefs and managing mangrove forests decreases the wave energy of tsunamis. So nature has a way of protecting these coastlines naturally. So if we're not out there ripping up the coastline and taking care of, instead we take care of the reefs, we take care of the mangrove forests that grow right along those coastlines, the tsunamis, while they still will do damage, won't be as impactful as they ordinarily would be. That's the idea that they're trying to convey here. All right, now there are things we can do to worsen the situation for ourselves, right? So we just have to face the fact that, we have to deal with natural hazards. There's floods, coastal erosion, wildfires, tornadoes, and hurricanes that just happen on Earth, and that's just something we have to deal with. When we look at this picture of Honolulu, you can see where the buildings are. The hotels are right there on the water. This is not a city that is set up for protection against a major tsunami event, right? If they got hit with a tsunami, it would be extremely devastating. Another issue is overpopulation. People must live in susceptible areas. Honolulu is a very, very large city on a very small island in the middle of the Pacific. In the Hawaiian island chain, Oahu, which is where Honolulu is one of the smaller islands. It's certainly not nearly as big as the biggest island of Hawaii. Most of the other islands are bigger. So, but we choose to live in attractive but vulnerable areas. We like beaches. We like to live in the mountains. And so there's consequences that come with that. Engineered landscapes increase frequency or severity of hazards. You build a river across a mountain chain, that roadside or that highway is just going to absolutely cause landslides, and there's going to be flooding events and all kinds of things. You dam a river, you suppress fire. Mining issues will tend to be a major issue. And of course, changing climate through greenhouse gases changes rainfall patterns, increases drought, fire, flooding, and storms. We've been seeing that especially in the Darfur region of North Africa. This is a major issue with climate change. But there are things we can do to mitigate the impacts of these natural hazards, right? Through smart engineering, right? We can build proper seawalls that will defend against coastal erosion. That's what we see right here. This is a massive seawall that has been constructed. And you can see the people are living right along the edge of this thing. Now, if a tsunami hit it, that's another story. But just a regular sea storm during just a typical weather event, it could probably take it. We could build more earthquake-resistant structures. They're expensive, and third world countries can't always afford to pay for them. But that's one thing we can do. We design early warning systems. This is something we're starting to do more with tsunamis. Volcanoes, we're working on it. We're getting much better at predicting volcanic events than we once were. Tsunamis, we're getting much, much better at. Still, there's too many people losing their lives in these events. We can preserve reefs and shorelines. We can have better forestry, agriculture, and mining to prevent mass wasting events. Some people would argue that better regulations need to be imposed. Building codes. Insurance incentives discourage developing in vulnerable areas. Right now we use insurance, especially government insurance, to encourage people to build in flood-prone areas. It's the flood in the United States, it's called the National Flood Insurance Program, where we actually subsidize insurance for people to live in dangerous areas. That might not be the best thing for us, right? So mitigating climate change may reduce natural hazards over time. All right, so that's just my quick introduction. It's a primer to the Earth and plate tectonics in general and how it's all kind of tied together. And everything in environmental science is happening on that canvas. Now, where we're going with this now is into evolution and biodiversity, because on that canvas of the Earth is life. What is life doing in response to the changes on Earth? That's where we get into evolution and biodiversity, and we'll leave you off with this image here from Charles Darwin's image from 1845, where he was looking at the finches of the Galapagos Islands. And we'll see you in the next video. Take care.